So on our quest to decide if a reaction has actually happened, we also like to know specifically what is happening to make the reaction happen. And the best way to show these is just to show some examples of them. What we like to do is we'll break down a reaction. So this is just like a reaction. You notice it has the phases in it. You notice that it's balanced, like it has the 2's in front, So you'll just take a regular reaction, and what you'll do is you'll break it down into a full ionic, and then once we get that one, we're going to cancel some stuff out, and you'll end up with a net ionic. So all I have to show you is how to write it when you break it apart. This is all based on that solubility chart. Like you probably were like, oh, I already did that section, so I'm done with it. Well, it's coming back. So in the solubility chart, when we looked at the different ions and we talked about how, if something is soluble or not, well, what we're really looking at is whether or not they split apart in water into positives and negatives. So this is a salt, and so salts do split apart in water when they say AQ, and they're going to split apart. This is going to split apart into a Cu plus 2 and a Cl minus, and actually it's not just one Cl minus, it's going to be a total of 2 Cl minuses. So it's Cu plus 2, and then there'll be a Cl and another Cl. So all of those are in the water. So when we write it as an equation, we'll write Cu2 plus, and then we'll say, okay, there's 2 total Cl minus ions. And then we'll also include the phase right there. And that's how we'll break this into its 2 parts. And you can see I already have this written here, but I forgot to put the AQ, so add the AQ right there. And we go piece by piece and we look at the different parts. Now as we look at this one, we've already got the phasing on it. If you didn't have the phase, you should look it up and figure out if it's soluble or not. So this is soluble, and it breaks apart into 2 pieces. Now what this is saying is that I have an AgNO3, and then I have another AgNO3, because it says that I have 2 of them. That's what that 2 in front means. So it means in the solution per reaction, I have an Ag plus, I have an NO3 minus, and I have another Ag plus, and I have another NO3 minus. So overall, I have 2 Ag pluses, and I have 2 NO3 minuses, and then I'll write them as AQ and AQ. Sorry, my AQs just look awful. So when you have a coefficient in front, you move it and you apply it to everything. But notice that this is a polyatomic ion group, and it always stays stuck together. That little 3 at the end doesn't affect him. So again, if you need to review your polyatomic ions, you can, just to make sure you know which ones stay stuck together. In contrast, when you have the little 2 over here, because all of these break apart, it only applies to the thing that it's beside. But again, this is a polyatomic ion group, and so the 3, this stays stuck all in. So that's what the numbers are doing when we're doing this. So try to keep that straight. Now let's look at this one. This is an AQ, and so this breaks into, notice there's nothing in front, but I do have a 2, and that applies to both of the NO3 groups. So it's like saying I have a Cu2 plus, and then I have a NO3 minus and another NO3 minus. So again, the way I write it is Cu2 plus AQ plus 2 NO3 minuses with AQs, because it breaks apart into positives and negatives. And then finally over here, this is a solid and it stays stuck together, AgCl, and it stays stuck together. We don't write it separated. So if you compare this to what I have written down, so you can see over here my Cu and my 2, there's my Cu right there. Here's my Ag and my NO3 section right there. Now this is missing something. You'll notice it's missing the 2, so we need to throw that in right there. This is also kind of intended to double check and see what might have been missed. And then my Cu is right there, and my 2 NO3 is there. And then here's my AgCl, and it's put together. So I have a few tips and a few things to notice. One tip is I kind of recommend ahead of time going ahead and drawing the little split lines where you're showing it all split apart. So I think that can be helpful, especially your first few times. And when you have something that's a solid, draw like a circle around it so you're not tempted to split it apart. And it also can be helpful to go ahead and write the charges of everything ahead of time, because then you're not thinking about it when you're trying to write out this big long reaction thing. And I don't need charges for this because it stays stuck together. The final thought is that everything on the left needs to have a match on the right. So if you'll remember, I put this 2 in here because I'd forgotten it. If I had left it out, there's kind of a checkpoint on this where it lets you check. You'll see a NO3 group here. Over here, on the other side of the arrow, there's a 2 NO3, and they're not the same because one has a 2 and one has a 1. So that tells me, oh, I probably forgot something. I need to look up, and oh yeah, I forgot that I should have put a 2 with that one. And then I stick it in. Also notice everything in this ionic, it has a charge. All of it has charges except for the thing that's a solid. So these should look very charge heavy all over across. Everything should also have a phase. And I think now finally that one is improved and is correct. And so that would be the full ionic reaction. And then finally, net ionic. So that's when you take the things that are the same on both sides. So like, for example, this and this, that's the same on both sides, so those get canceled. Let's look for something else, the NO3s. So that's the same on both sides, and that gets canceled. But this is not the same as either of those. So that's what's left. So here's our net ionic, and there would be a 2 right there also. So here's something that I can tell us that it's not balanced, and that got missed also. So there was a 2 in the front there, because there was a 2 in the front there. So sometimes you can go up and fix things that you might have forgotten every time. So make sure you've got this completely written out correctly. Now here's the other thing, is that net ionics have to be in the lowest coefficient. So even when you, cancel everything out, you'll notice I have a 2, a 2, and a 2. So I actually need to divide everything to get Cl minus AQ plus Ag plus AQ goes to AgCl solid. That would be the proper form. You can't leave it with these 2's in front. You just can't do it that way. It doesn't happen. And then also you could be asked about what are the spectators. Those are the ones that are canceled out. They're the ones watching the reaction. You don't have to say which, like how many. Like, you know how there were 2 NO3s? You don't have to put 2 of the NO3s. You're just saying which ones they were. There's the CO2 plus and the NO3. This is kind of a long explanation for something that is not as difficult as kind of it sounds explaining. Once you've done it a few times, it's kind of clear. So let's go through this other example right here. So the AQ, I'm going to split that there. I'm going to split that there. I'm going to split that here, and I'm going to split that here. And so that becomes 2 plus, that's a minus, that's a plus, that's a minus, that's a plus, that's a minus, that's a plus, and 2 plus, and then there's a minus. And then I've already got these written up, broken apart. So notice my 2 did end up in front, so that's good. You shouldn't have any like little sub numbers unless it's a polyatomic ion group. Notice that my 2 got put with the Na and the Br. Notice that my 2 got added to the Na and the Cl, so that's all good. And then I have my CaBr. Notice that the Br, it still has this 2. Everything has phases, everything has charges. And then I'm just going to find my matches. So there's a match. Here's a match. And again, part of this is just double checking that you haven't missed any numbers on the front. Right there and right there. Look how everything has a match. When that happens, what that means is that everything cancels out. If everything cancels, it just means that these are floating around in solution. They aren't doing anything. They're just floating. They're not making anything new. So that's no reaction. The net would still be the same as the, well, it would not be the same as the complete. The net ionic, you just really write no reaction. You don't write anything down for that. And if you want to know who the spectators are, again, you don't need to put the 2's in front. You're just asking who are they. Everything is a spectator. In a sense, the word spectator implies that something actually happened, that they're watching something. So in some people might argue that there were no spectators because there was no reaction. So one final little note that might save you some time. If you're just trying to figure out if a reaction is going to happen or not, look at the products. If both products are AQ, then that means no reaction. So you might be able to skip these extra steps if it just wants to know if there's a reaction or not. If, however, you make a solid, or if you make liquid water, or if you make a gas, a solid liquid or a gas, in one of the 2 particles, then your reaction is going to happen.